All right, guys. Good morning. How's everyone doing?
Pretty good. How are you?
Not too bad. Um, so just before we get started with the last part of plate tectonics, uh, we got news from the university that we're officially going back in person next week, which I'm looking forward to meeting you all in person, which will be nice. It'll be nice to have that interface as opposed to a screen. But just keep in mind, the Omicron variant still exists, so we are going to strictly enforce wearing masks indoors. If anybody doesn't have a mask, I'll try to have some spare masks. Just make sure to bring one with you. It's university policy. If you're not wearing a mask, I have to kick you out of that classroom. So make sure to wear a mask next week. We're meeting in Kirkbride Hall, lecture hall room 100. So keep that in mind, plan accordingly, same start time and everything. Also, I'm planning on keeping recording these sessions over Zoom because we have some students that are quarantining. So I want to make sure that content is available to them as well. So I'll still be recording these and posting these. These take up a lot of space on the Canvas site, so I'll probably shift these over to like a locked YouTube playlist. So I'll just give you guys the link to the YouTube playlist and then you can access all of those. That'll save some space for like lecture slides and other files that go on the Canvas site. So I'll be probably shifting that over this weekend, but those will still be available for the time being on Canvas. Make sure you finish quiz number 1. That's due tonight. If you need an extension, if you had some troubles, technical issues, let me know and I'll be happy to accommodate. Also, your in-class exercise is due on Saturday, so be sure to get that in. That one is graded manually by me. Canvas doesn't automatically grade it, so you won't know your grade immediately, but I'll be sure to get that to you as soon as possible. I think that's all the housekeeping stuff. So let's go ahead and get started with plate tectonics and let's finish plate tectonics. Next week, we're going to be doing earthquakes and tsunamis. So we'll get into more hazard stuff, more fun stuff. So stay tuned. Alrighty. All right, so we were discussing layers of the Earth. We were discussing the theories of plate tectonics and how that came about, why we understand the interiors of the Earth and why it's no longer a mystery to us. We know more about the density, the structure, the chemical composition of the different layers of the Earth and how those layers interact to create the surface of the planet that we live on today. So we're going to talk a little bit more about that in greater detail today. So we know, just to reiterate, the lithosphere we know is that really hard, rocky part of the crust and the upper mantle. It's the top part of that Oreo cookie model that we talked about, and it's floating on top of the asthenosphere, that creamy filling, basically. Still kind of solid, but a little more fluid. So all of these different parts of why is that such a hard word to say? Lithosphere are broken up into these large blocky tectonic plates that you see here. And each of these are labeled, and they're pretty self-explanatory as to where they are and how they're labeled. A couple of them might surprise you. There's the Nazca plate, which is just this random plate off the coast of South America, the Cocos plate right off of Central America, the Juan de Fuca plate up near the Pacific Northwest, as well as the Fiji plate, the Philippine plate. But then we have all of these larger, more stable plates that are interacting with each other. So we'll come back to this map a couple of times throughout this lecture. So just to get some review in, we looked at these Watt-Wadati-Benioff graphs last class. So just type in the chat which one do you think has the shallowest subduction. Remember, these are mapping earthquakes and the overarching path of a subducting plate. So go ahead and type in the chat which one you think has the shallowest subduction. All right, guys, very good. That answer is in fact C, which makes sense. They all have the same scale. If we have the same length and we're only going down probably 150 kilometers, that's got to be the shallowest scale in Peru. Let's see here. So why is this specific region right off the coast of Peru, why is it so shallow? So what we have here in this area is the Nazca Plate, which is oceanic crust. It's going under the South American Plate. The oceanic crust of the Nazca Plate is a lot younger and it's much hotter, so it's a lot less dense than some of the other continental crust. So it has a tendency to be a little more buoyant, so it wants to lift up a little more on the South American Plate on the underside. So this is going to keep subducting underneath, and as we mentioned before, the Andes Mountains, the second highest mountains in the world, they're going to continue to grow into South America and potentially even end up splitting Brazil with this big mountain range. So there are 3 different plates that meet at this subduction zone. Up north, we also have the Cocos Plate right off the coast of Central America, and those are diverging, they're spreading apart, whereas the Nazca Plate is converging at the South American Plate, they're coming together. So we're going to talk a lot about divergent and convergent boundaries here. So another review, let's take a look at this seafloor spreading map. What do you think is the youngest ocean floor? Get acquainted with, let your eyes adjust to the map itself. Remember, the gray is the continents. The colors are the sea floor. So go ahead and type your answer in the chat. Remember, we're looking for the youngest ocean floor. All right, guys, very good. Very good, you're paying attention. That answer is in fact C. That's right along this mid-ocean ridge in the Pacific, where new magma is coming up from the core, from the mantle. Those plates are spreading apart, allowing new magma to come up and solidify. Once it's solidified, it breaks apart, continuing to split and diverge, and new magma can come up again, and the cycle goes on and on. So mid-ocean ridges have some of the newest and youngest rock on planet Earth. All right, so let's go back to this for a second. So looking at this map, looking at the legend, we have a lot of different types of boundaries. Since these plates they're not connected, but they're interacting with each other, they're bumping into each other, they're going away from each other, they're sliding past each other. So we're going to talk a little bit about these types of boundaries. So let's look at the mid-Atlantic ridge right along the center of the Atlantic Ocean. It's a pretty complex divergent plate boundary. As you can see, it's spreading apart, but there are also these offsets in it. So it's not a perfect line of divergence. What you have at divergent plate boundaries is you end up getting transform faults, where the plates are sliding past each other and they're sometimes getting locked, and then they'll eventually break, and that can create an earthquake. But it's broken up into these segments, and that takes a lot of the stresses and a lot of the forcings of stress off of this whole plate system. We also have convergent boundaries denoted in red. You'll notice India into the driving into the Eurasian plate. That's where we get the Himalayas. We have this continental crust of India driving into the continental crust of the Eurasian plate, and that's why we have such high mountains of the Himalayas. We also have convergent boundaries from the Pacific Northwest of North America all the way up through Canada and Alaska. That's a very volcanic area. We have a lot of those mountains have developed from volcanoes, so that makes sense as well as with South America. That whole Andes mountain range is made from convergent plate boundaries creating volcanoes. So we're going to talk a little bit about each of these boundaries. So as we said, 3 different types of boundaries. We're going to start with divergent, which is what we see at mid-ocean ridges, which is what we see in the East African Rift Zone. The plates are spreading apart because the convection cells are pulling that plate into different directions. So they're going to pull apart, and all that heat from the asthenosphere is coming up and bringing in fresh material. It's going to solidify. So these areas are where the plate's spreading apart. Divergent, spreading apart. Convergent, coming together. These are areas where we get island arcs, mountain chains. We get a lot of volcanism at these. This is where we get our subduction zones, where one plate, which is more dense than the other, is going to subduct underneath and go back into the upper mantle, melt down, and end up entering the rock cycle again. We also have transform plate boundaries, which is where the plates are sliding past each other. These create the most earthquake-prone zones on Earth. San Andreas is an example of a huge transform plate boundary system. The rocks, as you can imagine, they're not like the rocks in these models where they're nice and smooth. The rocks are a lot blocky and they're angular. They've got chunks hanging out, so they're going to get stuck, they're going to get locked, but it's going to continue to build up pressure until that pressure is released and it breaks. So let's talk about these divergent boundaries first. In this model below, we're going to see the types that occur in ocean spreading centers, like the Mid-Atlantic Ridge. To the right, we have something that we see in East Africa, the East African Rift Zone, whenever we have a spreading center within continental crust. And these create different types of landforms and features, and they also have it takes a little bit more different time scales to form these from oceanic versus continental. So as we said, convection currents below the crust is what is pulling these apart. Those large-scale convection cells at other places are bringing plates together, but at this certain space, they're coming up and they're pulling them apart. And it's creating tensional stress. Good vocabulary to keep in mind, constructive margin. This is that center of the spreading ridge where that new crust is formed, where that hot magma is coming up from the center of the Earth. It's hitting the water, it's hitting the atmosphere at rift zones, and it's solidifying. And then once it's solidified, it's going to break apart as that tensional stress continues to pull it apart. So divergent boundaries form from super hot regions in the mantle. These end up breaking down parts of the asthenosphere and lithosphere. If you add heat to something, it's going to end up weakening the rock itself and enable it to react in a more elastic fashion. So the asthenosphere, because it's more elastic, we talked about, think of the Oreo cookie model that I keep mentioning again. It's that creamy filling that's going to be a little more elastic, a little more ductile, so it's able to be deformed. So this is going to end up deforming the asthenosphere, whereas once you get to the lithosphere, that hard, rocky top of the cookie, it's going to enable it to break. The lithosphere, since it's a lot more brittle, it tends to break rather than bend. So we're going to break a lot of those rocks using those pathways of the magma, and it's eventually going to collapse. So this is what it looks like after we've reached that collapsing point. As you can see, we get all of these different like large scale faults, all these hanging pieces of rock. We sometimes tend to get volcanic eruptions as well because the magma wants to get to the top of the surface. So you get a lot of volcanic activity, but you get a lot of faults and a lot of basins because as these are pulling apart, the rocks are falling in and they're melting and recrystallizing. So you're going to get a hole in the ground that's going to extend along that spreading center. So eventually the domes of these buildups are going to collapse after it melts. This is going to enable water to come in at spreading centers. This enables it free to move as it's pushed apart by all the rising magma. They're going to continue to stretch, continue to come apart. And at these types of boundaries, we do tend to get earthquakes. As you can see, we get all these faults, and all of these faults technically tend to draw earthquakes and have a lot of earthquakes. Because these are faults from pulling apart, these earthquakes aren't going to be very serious. Think of the earthquake that we had in Virginia in 2011. You can feel it, but it's not very serious. It's not going to cause a devastating tsunami. It's nothing compared to transform faults or subducting faults or subducting plate boundaries, because these are going to be large scale earthquakes. But at divergent boundaries, we get some earthquakes, we get some volcanic eruptions, but they're usually pretty gentle. A lot of basalt, because it's rich in those ultramafic rocks coming from the asthenosphere. So whenever we have divergent boundaries, we get something known as ridge push. So this gravity-driven force pushes the lithosphere away from the spreading center and towards subducting zones. So at either end of this diverging plate boundary, we're going to get subduction zones somewhere. So now we get to converging plate boundaries. This is where we get our subduction zones. So we can have oceanic convergent plate boundaries, oceanic continent plate boundaries, and continent plate boundaries. And these develop very different types of features on the surface, like mountain chains, island arcs, huge mountain chains like the Himalayas. They also create more earthquakes. So we're going to talk about those in a lot greater detail. So a lot of the different plates of the world contain mixtures of continental and oceanic crusts. For example, North America, mostly continental crust, but a good portion of it is oceanic crust. Once you get off the continental shelf all the way to the mid-Atlantic ridge, you're going to get a lot more oceanic, more dense material. Same with the South American plate. The African plate, as you can see, has a lot of oceanic crust surrounding it. So just type your answer into the chat. Which contains a higher density, do you think? Remember, higher density means it's going to sink more. So continental crust or oceanic crust, which has a higher density? All right, very good. So higher density rocks means we're getting those more magnesium rich rocks, those heavier rocks that tend to sink more. So the answer is definitely oceanic crust. So that's why the oceanic crust is creating those basins where the oceans can fill in with water. Continental crust is above the water line just because it's much lower in density. It can rise a lot higher. It can build up a lot more mass before it creates a lot of weight. So that's why we have continents versus oceans where everything sinks. So convergent motion creates compressive stress. divergence creates that tensional stress. Now we're talking about compressive stress. We're going to get um, different types of landforms and forces here. So subduction is obviously when happens when density is unequal. So the denser plate subducts beneath the less dense plate, the lighter plate. So whenever you're dealing with oceanic and continental plate boundaries, the continental plate boundary plate is always going to stay on top. The oceanic crust is always going to subduct below it because it's heavier. It wants to sink. It wants to go to the lower portion. Oceanic, it depends more on the chemical composition of each plate. One of them eventually becomes more dense than the other and sinks below it. As you can see in these two models, you get volcanism from the subducting plate. As that plate is being pulled into the asthenosphere, that plate becomes unstable. It starts to break apart, starts to melt, and that magma comes up to right up through either the continental crust or the oceanic crust of the overriding plate. And that forms those like long volcanic arcs. The image on the left would be a great example of the Andes Mountains in South America, that long volcanic arc that goes over the coast of South America. It's from that one subducting Nazca plate that's continuing to build up those volcanoes. If you have oceanic, you're going to get island arcs. Those volcanoes are still going to exist, but they're going to continue to build up from the ocean bottom until they peak out over the surface of the ocean and form islands along this long chain. So that's where we get island arcs along the Philippines, along Fiji, areas like that. That's where we get those long volcanic island arcs. So collision is what we get when density is pretty much equal. So if we have continental convergence, like we do with India and the Eurasian plate, right where the Himalayas are, since they're both continental plates, they both want to rise. And because they both want to rise, we're going to get a lot more buildup of continental crust. We're going to get the crust a lot thicker at that portion. So they just continue to pile drive into each other and build that rock up and more until one of them eventually starts to subduct, but it's going to continue to build up at the same time. There's not much volcanism. You can get a lot of earthquakes. There's a lot of instability there because of all the compressive stresses, but you don't really get any volcanism because the continental crust is so thick and stable. It doesn't preferentially melt right at the Himalayan zone. So this is what you get at subducting oceanic zones. What you end up with is that you get that volcanic arc that we mentioned, where the subducting plate is melting. It melts up through the lithosphere, but also right at the point of subduction, you can see you get a trench. And trenches are just where the overriding plate kind of gets locked and then it starts to kind of dip down with the subducting plate. So you get a lot deeper trench at these convergent plate boundaries in subduction zones. So trenches are often a really good indicator that a subduction zone is there. What is working? Okay. So in subduction zones, you're going to get a lot more deeper earthquakes, around 100 kilometers deep. Get a lot of great heat and pressure. The reason we have such volcanism in these areas is because the subducting ocean plate has a lot of water in it. As you can imagine, it's sitting underneath the ocean. Those rocks are going to eventually absorb fluids. Fluids and different types of gases that can stay in ocean water. So as that enters into the asthenosphere, it's going to melt. Those water and fluids are going to help accelerate that magma coming up to the surface. So that eventually breaks through the crust above, and that gives you that those volcanic arcs. All righty. So as we said before, South America is a great example of this. We have a couple of different volcanic zones in this area. So in the north, around Colombia, we have a northern volcanic zone. That's from the interaction of the Cocos Plate, which is next to Central America with the South American Plate. That's a convergent boundary. We have the Central Volcanic Zone in northern Chile. This is where I do some of my research. We have the Nazca Plate underriding the South American Plate, also giving us another volcanic zone. And then we have the Juan Fernandez Plate, which is also going under the South American Plate in the south. And so this is what's giving us these really high mountains in the Andes. Aconcagua is a very high volcanic mountain. Calbuco in Chile is another good one, which I think that erupted recently. But also, as you can imagine, these other subducting plates are sliding past each other to the north. So the Nazca is sliding past the Cocos Plate, so you get this transform boundary known as the Nazca Ridge. So you get a lot of sliding past each other. You get a lot of instability, creating huge risks of earthquakes. And if you have huge earthquakes in the ocean, you have a huge risk of tsunamis. So that's where the hazards portion comes into this. We talked a little bit about that. Okay. So deep sea trenches are subduction zones where we have oceanic crust meeting oceanic crust. Because they're both the densest portions of crust, they both want to sink, they're a lot heavier, and the added portion of subduction creates the deepest trenches in the world. So the Tonga Trench, Marianas Trench, these are formed at subduction zones. And they're the deepest places that you can enter on planet Earth. Well, enter is used lightly. We can get robots down to the Marianas Trench, but I don't know how well it would go getting people down there. So we get at oceanic crusts, we still get that island chain formation. So Indonesia is a great example. Sumatra is a very highly volcanic zone in the Pacific. Japan also was formed by oceanic subduction. The islands of Japan are also very volcanic and formed from volcanic action. And they also form along that same plate boundary. So the shapes of these islands are always linear and linked to the shape of that converging plate boundary. All right, so let's do a little test and let's see which plate is going to subduct. So keep an eye on the key here, the legend, and let's decide which areas are going to create subduction zones. So based on your choices here of these specific regions, which area, and using the legend at the bottom, which area is going to be a prime place to have a subduction zone? Go ahead and type it in the chat. All right, I'm seeing some different answers. So first, let's go through each of these answers and see if that makes sense. So the San Andreas Fault. San Andreas is right over here. We don't have a lot of convergence over here. There's convergence far to the north, but not along the San Andreas Fault. This is the transform boundary where the plates are sliding past each other. That's what's giving us all those earthquakes, those shallow earthquakes at San Andreas. So that's probably not the best answer. The Mid-Pacific Ocean. Mid-Pacific Ocean, we're talking about right over here, right over here. So we don't see a lot out there in the Mid-Pacific because that's the middle of the plate. So there's not a lot going on there in terms of plate boundaries. There are hot spots, but those are a different thing entirely. So probably not a good answer for mid-Pacific. Antarctic and the Indo-Australian plate. So here's the Antarctic plate. Here's the Indo-Australian plate. As we can see, those plates are moving away from each other. That's a divergent zone. So we may have a ridge, a spreading center ridge along that boundary, not a convergent zone. So the Philippines is probably the best answer, just because we have so much convergence there from the Pacific plate underneath the Philippine plate. So we're going to have not only a subduction zone there, but we're also going to have a pretty deep trench with oceanic and oceanic crust. So let's identify, let's take a look at the oldest crust in the world. So as you can see here, 180 million years ago, we start to form this portion of the Pacific plate. If we look at where the spreading center of the Pacific plate is, over here closer to just off the coast of South America, it makes sense for the oldest stuff to be on the exact opposite side of that. Now, we're not going to get anything older than 180 million years along this ridge, mainly because as it's subducting, it's being destroyed, right? So we can't access those rocks. We're not going to be able to study and test those rocks. Those rocks don't exist anymore because they're starting to melt. So we're not going to get anything older than 180 million years, because that's when that collision really started 180 million years ago. Right. We've gone over this stuff, All right, let's talk about slab pull a little bit, which is, even though that convection is what drives plate motion, slab pull is something that really helps with subduction. As you can imagine, whenever you have two massive rocky plates the size of continents, it's really hard to get motion going where one will subduct under the other. Slab pull is something that really helps with that. So since the slab is colder, because it's more dense and it's oceanic, it's going to pull into the asthenosphere, and it's also driven by that ridge push. So we have convection, we have ridge push, and we have slab pull. So the combination of these forces are going to help drive this motion and drive the subduction underneath the other plate. So subduction is, remember when we were talking about the rock cycle, where new rocks are formed at spreading centers. Eventually they can weather down, form sedimentary rocks. They can be pressed and squeezed until they're metamorphic rocks, and then eventually they enter back into the earth and melt down and eventually form new igneous rocks. Subduction completes this cycle. So we start with fresh rock at spreading centers. That rock travels across the entire plate until it subducts onto the other side. So the oldest rocks over here in the Pacific plate, 180 million years ago, formed at those spreading centers. And that plate grew and cannibalized itself underneath the Philippine plate. And that enters into the asthenosphere, it's melted down, it's destroyed. So that's completing the cycle, and then the cycle begins again at the spreading centers. Let's see if this works. All right, so this is a good model of what's going on with the Indian plate and the Eurasian plate right now. India used to be its own subcontinent. It used to be its own, kind of like Australia, just an island continent separated. Wasn't until a few million years ago that it went on a collision course towards Eurasia, and because they're both very, very low in density, they're building up the Himalayas constantly. And India is going to continue to drive into the Eurasian plate until it can't anymore, until there's not enough energy to drive that motion. So the Himalayas are going to continue to rise throughout time. So this is, since its initial contact, it's moved in 2,000 kilometers. Right before the collision, you have this like shallow oceanic basin. It's not as deep as the deeper Indian Ocean, but it's probably teeming with life. So you can imagine you get a lot of shells and remains of animals that end up in the sediment of those oceanic basins. As India continues to drive into it, it's going to solidify those into fossils. So this is one of the areas that we find oceanic fossils, sea life fossils. So this started to help develop the theories that contributed to plate tectonics, because if we have oceanic fossils that are in the highest places on Earth, that place at some point had to be underneath the ocean. So with this collision with India and Asia, we're developing the Tibetan Plateau. As you can imagine, Tibet, which is known for being very snowy, very cold, very high in altitude. This is a huge, huge thickness of the continental shelf. So people think that Tibet is going to become its new craton. Cratons are these really stable portions of continental plates. They don't subduct. They're really stable. They persist for a long time. There's one under North America. There's one under Siberia. So those are going to be around for long times. So we're continuing to drive India into the Eurasian plate, building up the Himalayas. So we're building up this huge accretionary wedge, which is just this wedge of accreted rocks and sediment. And this ends up deforming all the pre-existing rocks. So we get a lot of metamorphism here in this area, just because of all the pressures and all the different foldings and refoldings that occur in this area. All right, so let's go back to this again. Which one of these is going to be your convergent collision boundary? San Andreas, mid-Pacific Ocean, Antarctic, Afghanistan, or Indonesia? So where is that convergent collision boundary? All right, I'm seeing a lot of answers for D. That makes sense. That's correct. Well done, guys. Makes sense because Afghanistan is up high in the mountains. It's very high in altitude. Probably what you see a lot of in Afghanistan is from the news. You see a lot of dry weather. It's true, it's dry, but it's also very cold because of its altitude and elevation. All right. Oh. So now we're going to go into transform boundaries. Transform boundaries are where the plates are sliding past each other, and these boundaries occur at all sorts of places. As you can imagine, we can't just have divergence and convergence on a globe, on a circular surface. We have to have some sliding past each other in an imperfect way. So we're going to see a lot of transform plate boundaries all over the place. So this is where we get the initiation of shear stress. Shear stress is can best be imagined if you take a stack of index cards and you put your hand on top of it and you push it forward. That's a shear stress. You're enabling a force on a plane in the direction of that plane. So this is also known as strike-slip motion. You have the strike of these different plate boundaries surfaces, and they're sliding past each other. Nothing is, it's not destroyed, it's not creating new material. you're not getting volcanism like you get at diverging plate boundaries or converging plate boundaries. So you're not creating new rocks, but you are deforming existing rocks. But as you can imagine, with plates sliding past each other, you're going to get a lot of earthquakes and a lot of hazard risks for earthquakes. So if we look at divergent plate boundaries, whenever we have that tensional stress, we're also going to develop some shear stresses because having a long continuous plate boundary, divergent plate boundary along the Mid-Atlantic Ridge, for example, it would be really tough to do. So what happens is it's broken down into these little segments. It's not a continuous mid-ocean rift, it's a bunch of little mid-ocean rifts, and they're broken up by these transform boundaries that take a lot of that tensional stress away and convert it into a shear stress. So like all of these divergent boundaries that you see on this map, every single one of them has transform boundaries there. It takes a lot of the stress off, a lot of the strain off of the tensional stresses, and it enables the Mid-Atlantic Ridge and other spreading center ridges to continue to form. All right, so where do you think we're going to have a transform boundary based on this map? Alaska, the Antarctic Indo-Australian plate, the Alps, or Indonesia? All right, I'm seeing a lot of answers for D. So let's break each of these answers down. So Alaska up here, this is a convergence zone. So we're having stuff diving down and subducting underneath the North American plate. So that's why we have the Aleutian Islands, that volcanic island arc. That one's not a good example. We're not sliding past each other. We're diving down underneath a plate. The Alps is up here. The Alps are a very old system. We used to have a lot more convergence, not a lot anymore. So probably not having any sliding past each other. Indonesia, we have a convergent plate boundary. So we're diving down beneath the oceanic plates. Not a lot of sliding past each other. But if you look at the Antarctic plate and the Australian plate down here at B, we're seeing a lot of segmentation of this spreading center ridge. So these plates have to be sliding past each other at portions and not just spreading apart in all of them. So the best answer is probably going to be B. Does that make sense to everyone? If you need any help with understanding that, let me know. Because sometimes it's a little confusing with so much information on this map. But we'll continue to go over this and review it. So based on our map, we saw a lot of transform boundaries on spreading center ridges in the Mid-Atlantic Ridge, the boundary between Antarctica and the Indo-Australian plate. We don't get a lot of transform boundaries on land. It's very rare, but San Andreas is a great example. There's another transform boundary you may have heard of in Turkey, the Anatolian Fault System. That's a pretty common one. That's why they get so many earthquakes in the center of Turkey. But the San Andreas Fault, you have the Pacific plate just sliding past in this little segment of California, sliding past the North American plate. You get some rifting right in the Gulf of the Baja California, the Gulf of California. That's why the Gulf of California is there. It's rifting apart and sliding past each other. But San Andreas is one of the very rare locations on land where we can actually see the fault system, and we can see these plate boundaries sliding past each other. So this is what you get in this type of environment. You get a lot of rocky hills built up along these very long linear features. So as you can imagine, this is the fault system right to the right. So you build up all these tensional stresses and these shear stresses as you're sliding past each other. It helps to build up the landscape a little bit. But then you get a fault like this. So we're standing on one side of the fault. Keep an eye on some of the features here, like this river that runs through it. So there's the fault system. As you can see, that river is offset by, I wish I had a scale for this image. Sadly, I don't, which that would be very helpful. But we can see there's a clear offset in this image. So based on where we're standing, if we're standing on the lower part of the screen and we're looking at the other part of the screen, which direction has that landscape shifted? Has it shifted to the left or the right? Go ahead and type your answer in the chat. Okay, I'm seeing pretty much 50-50 split. So this is the basic rule that we use when it comes to establishing which direction things are sliding. Oh, there it is. So if we see this river, and originally it was obviously together, now it's offset. If we're standing on either side of this, we can see, and we imagine the other side of that fault moving, whichever direction it is displaced, that's the direction that we're talking about. So if we look at this direction and we say, okay, it's definitely moved to the right. That would be the same if we were standing on the other side. It would definitely have also moved to the right. So it doesn't matter which side of the fault you're standing on, just focus on which side that you're viewing it from in the moment, and whichever way the other one has displaced, that's the direction of motion. So this river has displaced however many meters to the right, based on where we're standing. So just a quick summary. We know we have the lithosphere, top of that Oreo cookie. It's broken into a bunch of different pieces called tectonic plates, and they're moving on the surface of the Earth, and they're interacting with each other. So the plates are creating new rock at mid-ocean spreading centers at divergent plate boundaries, and they're being destroyed and cannibalized at subduction zones where it's diving back into the Earth. The boundaries between these tectonic plates are very active in their hazards, volcanically active, seismically active, a lot of earthquakes as well. So plate tectonics has helped us to really map out where volcanoes are and where earthquakes are, and why it makes sense for them to be there. So in geologic terms, plates move pretty quick, so ranging from 2 to 3 centimeters per year to 70 centimeters per year. 2 to 3 centimeters a year is roughly the time it takes for your fingernails to grow. It's the same rate. It's not usually a very steady rate. It doesn't just continually dive down. As you can imagine, rocks get stuck on each other. So it'll stop for a bit and then it'll suddenly be displaced, creating an earthquake. So these things aren't just a constant flow of events. It's just sometimes you get a little bit of motion, and sometimes you get no motion, and then all of a sudden you get a lot of motion. Breaking down our plate boundaries, When we have divergence, where plates are moving away from each other, we get some earthquakes, some volcanic eruptions, but they're usually nothing to write home about. There's nothing that really concerns us, just because they're very mild, they're small magnitude, they're not very damaging. Transform boundaries, where the plates are sliding past each other, a lot more damaging earthquakes, a lot more frequency. So higher intensity, higher magnitude. Convergent subduction, where we have plates subducting underneath each other. We can have a lot of volcanoes, but they're pretty infrequent. We also have earthquakes, some of the biggest earthquakes, but they're not as frequent. So high magnitude, low frequency. And of course, because these happen a lot at oceanic zones, we have a high risk of tsunamis. Convergence, where we have India slamming into Eurasia and creating the Tibetan Plateau. We have very strong earthquakes, very high frequency, very strong, just because of all the buildup of rocks. So why don't we take a 10-minute break, meet back at 11:05, and we'll come back to this and do a little review. So yeah, see you back in 10 minutes. All right, guys. So let's get back into this. Just a few more slides. Probably won't take the whole rest of the period. So, oh. All right. So real quick quiz. Let's look at the plate boundary near Delaware. Delaware is marked by that black asterisk. So what best describes plate boundary near Delaware? All right, guys, that looks exactly right. Delaware isn't near a plate boundary, and Delaware hasn't been near a plate boundary for quite a long time. That's roughly 1,500 miles to the closest plate boundary at the Mid-Atlantic Ridge. So this is part of the reason why Delaware, a lot of its hazards aren't related to tectonics. It's so far away that anything that happens at plate boundaries, specifically the Mid-Atlantic Ridge, isn't going to affect Delaware at all. So when it comes to tectonic risks, Delaware is really low on that totem pole. So let's talk about what's happening in East Africa, which Adam brought up right before the break. We have some type of plate boundary developing there. So what do you guys think that is happening there? Go ahead and type it in the chat. Oh, is this not a, this isn't a, is this a quiz? It is. Okay. So out of those four options, all right, very good. So we're getting a lot of, we see these divergent zones here in this divergent boundary. So eventually this is going to pull Africa apart. Most of East Africa is going to form its own plate just because of the tensional stresses pulling it apart. Some features that you can see on the continent of Africa that resemble this motion are a lot of Africa's Great Lakes in this area here, like Lake Victoria is part of one. It's basically this big basin. So yeah, divergence is eventually going to pull it apart. If any of you didn't hear Adam's question, he asked about volcanism in the area, because we know we get magma coming up to the surface at divergent boundaries. We do get magma coming up to the surface in the African plate, but because the African plate is, Africa is a continent, it's continental crust, it's a lot thicker. There's not a big threat of active volcanism or volcanoes in that area as of yet, because this is still a pretty young rift system. It's going to continue to rift apart, so volcanism may start to come up to the surface, but it'll look more like Iceland, where it'll just like leak out. No real, you're not going to have to evacuate. You're not going to have to divert lava flows. It'll be pretty slow and gentle, so it won't be too much of a problem. All right, so this one's a little more complicated. So which way is the plate moving if the red dots mark the most active volcanoes? So now we're talking about hot spots below the plate. And these hot spots stay in place while the plate moves over top of it. So the latest one, for example, is Hawaii. Hawaii is younger than Midway. So which way would the plate have to be moving for these island chains to form? All right. Seeing some A's, a lot of B's. Okay, so it's actually A. So this is something that's very, very difficult to visualize, because we're looking at the surface of the Earth, but the surface of the Earth is what's moving. So if we have, let's look at Hawaii itself and just the general shape of Hawaii. Each of those islands is formed from the same hotspot. So the latest one is the island of Hawaii itself, which is the biggest one, which is where Kilauea is and Haleakala is, these very large shield volcanoes. So if Hawaii is the youngest and Kauai is the oldest, that means that the plate had to be moving from Kauai to Hawaii, which means that while the hotspot is staying still, the plate is moving up to the northwest. Does that make sense? So we're imagining the hotspot, just this big ball of hot magma staying still. The plate is moving over top of it. It's depositing Kauai, then it shifts, it's depositing Oahu, it shifts, it's depositing Molokai and Maui. So that's why it's moving in this direction. That's how we map things out. The youngest spot at Hawaii is its most recent. So don't feel bad if you got that one incorrect. This is a very difficult thing to visualize and rewire your brain to think about. So let's talk about the layers of the Earth and how those materials react to stress. So as you can imagine, greater forces forces increase as you get closer to the inner core. Whenever you load a material with a force, you get pressure, and that force produced is called stress. So stress is going to increase as you get lower and lower into the different layers of the Earth. So just look at the graph here. That's a pretty standard curved graph of how forces are interacting in the lower mantle, the outer core, and the inner core. So these stresses tend to help deform and break down different Earth materials. So whenever we're talking about characteristics of different Earth materials, the two terms we usually use are elastic and ductile deformation. So elastic is just like this rubber band here. It's able to stretch and you're able to recover it. It returns to the original shape no matter how much you stress it, no matter how much you pull, it's going to snap right back to its original shape. Ductile deformation is more permanent. So if you apply that stress over a long time or over higher temperatures, you're going to completely deform that. So that's a piece of Laffy Taffy. If we bend that, it's going to stay there until it's bent back. And if it's bent back, it's not the same shape that it was before. If we pull that Laffy Taffy, it's going to continue to stretch and it's going to stay stretched. So that's ductile deformation, where it's still able to apply the stress, but it's never going to be able to return to its original shape. Now we have brittle deformation. So if we take that Laffy Taffy and we froze it, and then we slam it down onto the table, then we're gonna completely break it. That's a very, very hard force applied in a very short amount of time, and that's when we get that shattering effect that we see. So whenever we get to what's known as the yield stress is that exact point where deformation starts. So you can, if you can imagine, I can take a rock and just take any old rock and I can just start to put it in a press, and I'll just keep pressing and applying more force and more force. And eventually there's going to reach a point where it's going to break. That point is the yield stress, whether that's the point where it starts to deform ductily, whether it starts to bend or starts to break, that's the point of no return. All right, we talked about this. So let's talk about the behavior of some of these materials. That image to the right is saltwater taffy at a taffy place being made. And as you can see, saltwater taffy is a solid, but we just define it as kind of a plastic because it's a solid that flows. It's put up into this sloped tube, and then it just kind of gently flows down and stretches, and it eventually creates these patterns that you see here. So this happens over a short period of time for saltwater taffy, but as you can imagine, we have other features like glaciers that flow in different ways. So even though the glacier is made of solid ice and debris, it's still flowing and still taking the shape of the valley. It's creating a trough and it's driving down. So it still has viscosity and it still flows similarly to a liquid. So those types of forces are acting upon the Earth and are active within Earth materials. So what parts of the Earth have brittle deformation? So definitely the lithosphere. The lithosphere and the continental crust, the oceanic crusts, these are solid rocks. They're a lot colder. They're not exposed to as much heat, so they're definitely more brittle. If you imagine just mining operations, they're not stretching things out of the mountains. They're breaking them apart. They're blasting them. They're taking advantage of that brittle deformation, hitting the points where getting the stress to the point where it'll break, so they can remove whatever they want, whether it's rare earth minerals or coal or iron, stuff like that. So then we get to a more transition zone with more brittle and ductile. So that's where we get down to the asthenosphere. We get asthenosphere is more plastic. Imagine that glacier or that Laffy Taffy. It's a little more able to flow. It's a little it's able to be deformed without breaking. It experiences a lot more higher pressures. Then you get back to more rigid formations in the lower mantle, which are still able to be deformed, but have a little bit more brittleness, a little more ductile, not so much elastic. So just to reiterate, this is all of plate tectonics, and this is the foundation of all modern geology. This is in terms of geology, it's relatively new, but this whole theory of plate tectonics explains almost virtually everything on the surface of the earth and how it works. So the reason why we have fossils on the same fossils on South America as we do Africa, the same fossils that we have in oceans as we do in the Himalayas. It explains why we have glacial deposits in tropical areas, in areas that are tropical now. That means that at some point those continents were further south or further north, where they were able to experience that colder weather that allowed for glaciers to exist and affect the landscapes. It explains the movement of continents and why continents can fit together like puzzle pieces, which can help us in forecasting, not predicting, but forecasting how those continents are going to move and how that's going to affect life on Earth. And it also helps to explain why volcanoes are where they are, why earthquakes happen where they do, why rift zones exist in certain areas, mountain chains, and why hotspots are located in certain areas. So this is a huge theory. It's hugely complicated, but when we break it down into simple components, it's a lot easier to understand, and it'll help us explain certain hazard risks. And going forward in the class, it'll definitely help us figure things out. All right, so last one, layers of the Earth. We have the outer core and the inner core. We've gone through the lithosphere, the asthenosphere, the mantle, that last parts of the Oreo cookie. Now we're getting to the outer core, and the outer core is liquid. It's still very, very hot, incredibly hot, which is why it's liquid. It's melted down at around 5,500 degrees C. It's still very thick, very dense, mainly because of its composition of iron and nickel, and there's some sulfur in there as well. Then we get to the inner core, which is incredibly hot, but because there's so much pressure, we're getting that solidification. We're getting just this perfect ball of iron and nickel again. Still pretty thick, much more dense, which enables it to be a little more solid. So I kind of gave you the answer to this. Why is the inner core solid but the outer core liquid? Go ahead and type your answer into the chat. That shouldn't be the last thing we have today. All right, well done, guys. The answer is C. It experiences a lot more pressure than the outer core. They have the same, pretty much the same chemical composition, 90% iron, 10% combination of nickel and sulfur. So they have the same chemical composition, but because there's so much more weight on top of it and so much more pressure, that's what gives us a solid inner core and a liquid outer core. All right, so that's all I have on plate tectonics. Next week, we're going to move into actual hazards. So we're going to talk about earthquakes first, talk about P&S waves, the velocities of those, how we can predict earthquakes, and why they're located where they are. Remember, we're going to be in person for the first time. So number one, bring a mask and wear it properly. Number two, I haven't seen the room yet, but it's a lecture hall. So since there's only 35 of you, we should be able to spread out and get some distance in between people. Also, don't forget your quiz 1 is due tonight. Your second reading assignment is also due, and your in-class exercise is due as well. But that's due tomorrow. So keep that in mind, get those in. If you need help, let me know and just send me an email. I'll be happy to help. Otherwise, looking forward to meeting you all in person, and have a great weekend. Enjoy the weekend. Have a good one.
Thank you. Have a good weekend.
Thank you. Have a good one. Appreciate it.
Thank you.
Thank you.
Quick question. Which
Quick
ones
question?
did you